Okay, so I'm gonna start the recording and hopefully, let's see, it looks like I'm recording. Let me make sure my audio is working. My audio is working and I am sharing the screen, right? Sharing a notification, so I should be good. Okay, excuse all these pages that are open. I'm trying to make sure, based on what I'm covering today for the first video, I want to make sure I have charges on here so we can keep referring to them to make it easier. Okay, so we're starting with chapter 19. In chapter 19 of Chem 1412, we are dealing with electrochemistry. 1411, we should have focused on thermochemistry, talking about bonds and bond energy, bond breaking, bond forming, and the enthalpy of the reaction from bonds and everything like that. 1411. In 1412, we're looking at electrochemistry. So before we go into the details of this chapter, I have a quote unquote review session that we're going to go over to review what redox reactions are from 1411. So in 1411, you should have covered redox reactions. Okay? And if you remember redox reactions, read essentially red stands for reduction, and then ox stands for oxidation. And I actually think back to the lecture I had this week. I didn't really talk about Leo goes Gur, but anyway, remember Leo goes Gur from 1411 where it says loss of electrons is, ooh, I can't spell, oxidation. Well, yeah, it's hard to write vertically like that. And then gain of electrons. So gaining electrons is reduction, right? I probably should have written it somewhere, but you all know how random I am, so here it is. So Leo goes GER is an acronym that helps to remember. Loss of electrons results in oxidation in the chemical reaction. Gain of electrons results in a reduction in the overall chemical reaction. So these are essentially a yin and yang relationship where oxidation usually goes with reduction. So they're paired together, with oxidation part being the electron maker and then reduction part being the electron user. Okay, so this is a brief overview of 1411. So in defining electrochemistry, we're seeing that electrochemistry deals with electricity. So we know that electricity is formed when you have electrons moving, right? Moving through a system, either moving through a liquid, moving through a conductor, or moving through an atmosphere, right? But in this case, once again, moving electrons generates electrical energy, which results in electricity. So we're told it's the branch of chemistry that deals with the interconversion of electrical energy and chemical energy. So we're not only looking at electricity in general, we are looking at where electricity comes from. So from this statement here, we're seeing that chemicals convert into electrons by releasing electrons, right? And electrons ultimately yield electricity. City. Yeah, I have poor planning. Cause yeah, more like poor spatial awareness, right? Electricity. Let me write over here. Right. So the idea is you can go in the forward conversion from a chemical, get the chemical to release electrons, the electrons traveling generates electricity, or you can do the reverse. And in the reverse, you're pretty much using electricity to take up electrons to deposit chemicals. So that's how the reverse reaction takes place. Electricity takes in electrons, and well, usually electricity helps another chemical. So I should say here, the electricity in the reverse pathway, the electricity is the facilitator to help another chemical take in electrons to form chemicals. So it's not really as simple as I said it at first, okay? But we'll look at that later on in the chapter. So what we're going to be looking at once again is redox reactions. We're going to be looking at electrochemical processes that are called redox. You have oxidation, electron maker, reduction, electron user. I'm saying this in the beginning so when we get to it, we're more familiar with the process, okay? So I'm just trying to check to see if somebody has signed in. Okay. So moving on, we're told here in redox reactions, electrons are transferred from one substance to the other, okay? So here we're looking at how oxidation and reduction are defined. Remember, when these two are said together, because chemists usually get tongue tied, and they're not really that great, in my opinion, with terminology. They use the term redox as a short way of communicating reduction and oxidation versus saying that over and over again. Reduction, oxidation. That's kind of a lot to say. They just say redox. So you have reduction being represented here and oxidation right here. Okay, so what exactly is an oxidation process? How can you tell something is being oxidized? The most obvious way I would say here is, let me start with the most obvious way. When you have a chemical being reacted with oxygen. So you have a chemical or a compound. It doesn't have to be a compound, it can be an element too. So I would say here, instead of saying compound, I would say just a random chemical because it could be an element or a compound that takes on oxygen. So you have oxygen as a reactant. I'll give you guys an example here. Take for example, sodium as a solid reacting with oxygen as a gas. And together you get sodium like that. Okay. In this case, that will be an example of oxidation. Of course, you want to balance this, right? You put two here and that works out. So that would be an example of oxidation. And then we're told that oxidation is also a compound losing hydrogen. So if a compound in the chemical reaction has less hydrogen, that will be oxidation also. Now, these two definitions, while we do talk about them, those of you who are going over to organic, that will be Chem 24, 23, you will be majoring, you'll be focusing on these observations to define oxidation. Okay, you will look at an organic compound gaining oxygen and you will define that as oxidation. And the same organic compound can lose hydrogen and you will define that also as oxidation. Okay, in this class, general chemistry, we're just defining oxidation in general, hence general chemistry, right? Okay, what we measure on or what we focus on is defining oxidation by tracking how the oxidation number changes during the chemical reaction. So we're told here the oxidation number, and we talked about the rules of identifying what the oxidation numbers are in the different elements in the compounds in 1411. I will go ahead and review that in the beginning of the chapter after I go through the definitions, okay? Oxidation numbers can be tracked. And if you notice them increasing, we can say that that process is oxidation because oxidation process tend to favor increasing oxidation number. Okay. And then for the other side, reduction tends to happen whenever the oxidation number is decreasing. But for right now, we're focusing on oxidation, correct? Okay, so we're told here if an element loses electron, like I told you guys before, Leo, right? Loss of electrons, oxidation. And then we're being told here when we're looking at balancing the redox reaction, a half reaction has electrons as products. When you have a half reactions, where a half reaction where electrons are products, that half reaction gets defined as oxidation. So we'll be looking at all of these factors. I know it's a lot of definitions for just one term, but it's very important for us to know what we are looking at. Are we looking at an oxidation process or a reduction process? That's very important in how to balance your chemical reaction. Okay. Once again, we'll be focusing on this process here and then this part here and this part here. For those of you who are going to organic, I'll label that part here. You'll be focusing on this definition of oxidation in organic chemistry. Okay, moving on. The other part of oxidation is reduction. So what is reduction? Reduction happens when, I'm going to start with the organic definition first. When the compound is losing oxygen, so it's becoming less oxygenated, right? And losing oxygen. Or a compound, it can be chemical, it can be element too, that is gaining hydrogen. If it's gaining hydrogen, it is actually being reduced. Remember, reduction is sort of the opposite of oxidation. Not entirely, but in most cases, it seems like the opposite of oxidation. What we will be focusing on, once again, is not these two. These two will be focused on by Chem 24, 23. This is organic 1, or right here, organic chemistry. Our focus will be on tracking the oxidation number once we review how to assign those numbers. Okay? If the oxidation number decreases, that is reduction. So let me let you all know, right? You know how I like telling on myself? I'm not ashamed of my journey and my struggles with chemistry because you know what? That was part of my history, or should I say her story? That was part of my experience. It wasn't very easy. And the reason why I share this is not to say that you guys are exactly like me, because somebody called me out yesterday in class and said, "We are not you, professor." I said, "I never said you were." When I share my experiences and my struggles, it's just to let you know if you feel like you're struggling with something in chemistry, you're not alone. I faced that too, and I overcame, right? I overcame. So hang in there because it does get better. Just keep at it, keep working at it, keep working problems out. It does get better. Okay. Anyway, what was I saying again? Oxidation number of elements decreases. So when the oxidation number decreases, then you know that you are dealing with reduction. So for me, I was like, I'm not gonna remember this, y'all, because my recall is not that great. So I replaced the word decreases with reduces. So when you have a reduction in oxidation number, that is reduction because you kind of use the term here, right? See? Or if an element gains electrons. So the side that is reduction tends to be a little bit more positive, and we'll look at that later on, okay, in balancing the reaction. A half reaction that has electrons as reactants is also called reduction, okay? I'm a little distracted here because I'm actually at a meeting. Well, I'm logged in with my phone, so I'm kind of looking at my phone a lot to make sure that the meeting isn't over. Okay, let me check and see if somebody has joined me. Oh, okay, Ruby's joining me. I was hoping she would. Okay, so where are we at? We're moving on from here. Oh, yeah, this is fine. This is fine. I'll move on. So let's get to the rules of assigning oxidation number, part one. So the rules say here, you want to make sure you're looking at these rules and the order of priority. It says here the rules are written in the order of priority. I'll tell you this, that is true, as in when you're looking at a redox reaction, you're trying to balance it, you want to apply the rules in order, starting from rule 1, rule 2, rule 3, the 3A, 3B, 4A, 4B. You want to go in that order, okay? I would say you want to go in that order. You want to look at your overall reaction. If you have an element, then you want to apply the element rule to the element, right? And then if you have a compound, then this rule and this rule won't really work. You want to go straight to 3. Okay? So let me go over the rules first and then I'll kind of classify them. Uh, Rule number 1 says you want to look at your equation and see if you can find a free element. So what exactly is a free element? Now this slide here kind of shortens the description. A free element is an element that is in its standard state. So I'm going to give you guys some example. Regular elements like metals, such as magnesium by itself, will be like this, magnesium solid. So these are essentially elements or free elements. Free elements, and they have to be in their standard state. So the way I connect with that statement is essentially how you would find them in nature. So magnesium is usually found as a solid. Usually it's combined with something, but when you finally isolate it, it'll be a solid, right? If you find chlorine, it will be a gas. If you find iodine, it will be diatomic, also a gas. So with the Brinkelhoffs, you have to write them as Brinkelhoff, right? Just in case you're wondering, Brinkelhoff, yes, Br2, I2, N2, Brinkelhoff, right? Brinkelhoff. So 2, 2, 2, 2. All of these elements have to be written like that to be in their standard state. You get the idea, right? Now, when it comes to the other elements, the ones that are metallic, they have to be written the way they normally exist by themselves in nature. So if you're dealing with aluminum, aluminum will be monoatomic by itself in a solid state. Let me think of something else. Ooh, potassium. You get the idea, right? If it was mercury, mercury will usually be like a liquid. So you want to, once again, you want to look at an element in its standard state. Okay. Once again, for each of these chemicals, you assign the oxidation number of 0. So I mentioned this in class yesterday that the oxidation numbers sometimes overlap with charges, but they're not charges. These are numbers that are kind of like placeholders. They are arbitrary numbers, right? Made up numbers. When I say made up numbers, that kind of throws people off. One semester I was teaching this class in 1411. I was teaching the assigning oxidation number 1411. I had a nursing student who was so upset with me because I used the term made up. I said, yeah, they're arbitrary placeholders because in real life, the lecture notes are written after the lab. The scientist goes to lab, does experiments, gets experience and gets results, and then from those results the content in the textbook are written. But we are supposed to come to the same conclusion that they did, even though we haven't had the experience. So to bridge that gap, right, of experience, sometimes they make up stuff to kind of help us go through the same thing they went through without actually doing exactly what they did, so that we can come up with the same conclusion. So yeah, they're arbitrary stuff to help us come to the same conclusion, made up stuff. Okay. Anyway, so oxidation numbers are made up numbers. They sometimes overlap with charges, but they aren't necessarily charges. That's why they flip flop. What is the purpose of oxidation number? Purpose of oxidation number. So if you're making up stuff, you're making it up with a purpose, right? The purpose here is to identify, is the reaction being oxidized or not? Is it being reduced or not? So purpose of oxidation number is to determine oxidation and reduction. So we're trying to figure out, looking at a chemical reaction, is this reaction being oxidized? Yes or no? We can't really just look at it and tell. If the reactant is being added to oxygen, you could use that. But what if there's no oxygen? There's no obvious oxygen being added. Then we rely on oxidation numbers. Okay, so they're means to an end. The end is figuring out oxidation and reduction in a chemical reaction. That's the first thing. Second thing, we assign these oxidation numbers to elements. The element could be in a compound, but you have to assign the numbers to the element in the compound. Okay? So even though there's the overall situation that's happening with the compound, the overall oxidation number, we tend to assign it to the elements. Now that I've stated that, we can move on. So let's see. Ruby, I saw that you logged on. Let me see. If you do have any questions, feel free. I can't see the text screen right now, but I think I'll hear it if you do have a question. You can feel free to speak up. Okay. So I'm gonna go off script and kind of just give examples here as I talk through the rules. Then we'll come back and look at the rules to summarize what I just discussed. Okay. So rule number 1 applies to you looking at the balanced equation. So you want to go ahead, either you're looking at the balanced equation or you're looking at the equation you're about to balance, right? And you're looking at a formula. The first thing you want to do is go to the easiest formula. So first thing you want to look at is the element. If your element is in the standard state, so element in standard state, has an oxidation number of 0. Okay, I gave you guys examples earlier. So I'm going to say here, if it's magnesium by itself as a solid, this would be 0. So one other way you can look at this is kind of like the overall charge of this element by itself, since there is nothing written here or here, is 0, right? Because there's no number around there. So it's 0. And then for the non-metal, you have to make sure you obey the rules. If it's a Brinkerhoff, you want to make sure that it's diatomic molecule. So I'll use nitrogen here. Nitrogen as a gas. This is a standard state. So this will be 0. Once again, there's nothing written around here. Okay. Moving on. Rule number 2 applies to monoatomic ions. So when it says monoatomic ions, this is referring to ions that are made up of, these are ions, right? Ions means that they have charge. They either have a positive charge or negative charge. And they're monoatomic, meaning made up of one element or consist of one element. That's why it says monoatomic. So you have a species that has a charge, but it contains one type of element. Okay? In this case, I can say chloride here, phosphide here, let's see, aluminum here. And the oxidation numbers on these are equal to the charge. Okay? So in the monoatomic ions, oxidation number equal charges. Okay? For the first one, let me highlight the rule here. Oxidation number equals 0. Because first of all, if you look at the way the formula is written, there's no charge around it, right? No positive or negative, no number. So, and I mean the superscript, not the subscript. Okay? On this one here, you do have this charge right here, and that will influence the oxidation number. Once again, we're doing this because, give me a moment, let me log off of this meeting. So I don't have to, okay. So according to them, I showed up. Don't say anything. Okay, so moving on. They make a recording of the meeting. I'll watch it later. I can always do that one later. Okay. Anyway, oxidation number equal charges. So with that being the case, I'm going to write here the oxidation number of chloride with a negative charge is -1. So when I was in school, my teachers wrote the oxidation number in circles. Sometimes I do, sometimes I don't. But I used to wonder why, and I realized they wanted us to not confuse the negative here with the -1 here. Okay. So yeah, -3. You can write as -3 or 3 negative. Either one is fine. +3. Okay, so the oxidation numbers here match the charges, and I'm going to highlight that that's the rule we're using for rule number 2. Okay, so by themselves, the elements have oxidation numbers of 0. If they are monatomic charges, the elements have oxidation number that matches the charge. Okay, rule number 3. Ooh, rule number 3 has to do with compounds. So with this one here, we're dealing with, I shouldn't really say compounds, but it has to deal with polyatomic situations, right? In this case, we're dealing with either compounds, so you have many atoms combined together, compounds, or polyatomic ions. So what do these have in common? They have many elements combined together chemically, right? So how do you handle that? Let me give the general rule for ionic compounds, then we'll come back once again and look at this and summarize it. The general rule for ionic compounds. So if you have ionic, so for most compounds, let me say here, for most compounds, assign the oxidation of the non-metal or surrounding atom first. That's a long statement, right? Maybe the comma doesn't belong here. I'm not good with grammar. When we learned English at home, we didn't learn all this stuff. I mean, we did. Let me not blame my teachers. We kind of did, but it wasn't really very enforced. So I'm forever struggling with that. Anyway, for most compounds, I say here, I guess, for most compounds, assign the oxidation of the non-metal or surrounding atoms first, right? Then assign the oxidation number of the metal or central atom. Okay? Right. I'm supposed to be making things easier. I'm using air quotes and y'all can't see. It just makes me feel better. But yet I wrote all these words. So what do I mean by this? So in rule 3A, we deal with compounds. So let's look at how this plays out in compounds. And I'm going to start with regular compounds, right? I'm going to start with ionic compounds and then give you guys an example. So ionic compound. If you have an ionic compound, and for my ionic compound, I will not use the group 1A or 2A metal because there's a rule for them in rule 4, 4A and 4B. So I'm going to use something like aluminum oxide, like that, aluminum oxide. Okay, so how do we figure out the oxidation numbers of the elements in aluminum oxide? First of all, we have two elements, right? The first one is aluminum, second one is the oxide, like that. Okay, for this purposes, is it okay, y'all, if I write 2 here and I write 3 here? I'm just trying to show you to keep track of the number of atoms we have within the compound. Okay, so I'm going to try to follow the rule I wrote here. For most compounds, assign the oxidation number of the nonmetal first. Okay, so the nonmetal is this one here. This is a nonmetal. This is a metal. So I'm going to do that. I'll do the nonmetal first, right? With the nonmetal, you actually want to assign its charge, its regular charge. So here on the right, I hope you all can follow my mouse. I have the charge of oxygen based on the group number. Oxygen is in group 6 and it normally forms a charge of -2. So oxygen will gain its regular charge as its oxidation number. So I'll write here -2 for the oxygen. But look, to build this compound, we had to recruit or bring in 3 oxygens. Each oxygen brought in an oxidation number of -2. So I'm going to draw all 3. Okay? And this represents 3 oxygens, according to this. Correct? If you look at the whole compound does not have a charge. So what we're seeing here is when you add all the components, when you add the oxidation numbers of all the components in the formula, the total must be an oxidation number of 0. So I'm going to write here the total oxidation number in a compound, because compounds have no charges, right? Must be 0. This is non-negotiable. Okay, so right here, oxidation total for the whole compound must be equal to 0 because it has to match the overall charge, and the overall charge in the compound is 0. Therefore, total oxidation number must be 0. Okay, so once again, the non-metal oxygen gained an oxidation number of -2. That's it right here. But we have 3 of them. Okay, so for the whole compound to have an oxidation number of 0, what must the 2 aluminums be? So this is 1 aluminum, this is the second aluminum. Let me see. Oh, can you answer that, Ruby? If the total here on the right is -6, and we need the total on the left to be +6, what must each aluminum be?
Would that be 2? No, wait. Because each of those are +2, right? Or I mean 2, 4.
Wait, we're talking about the aluminum, not the oxygen part. The oxygen part is done, right? We want each aluminum to add up to give us +6. +3. Each has to be +3. Do you see how that plays out?
Yes.
Right. Since you only have 2 aluminums in the compounds, each aluminum has to be +3. Since you only have 2 to work with, right? So +3 gives you +6 total. But you have 3 oxygens to work with, and each oxygen is -2. Okay, it takes a while to kind of adjust your mind to kind of to follow along with this one here. It just so happens these oxidation numbers we assigned are the charges. When you look on the right here, aluminum is +3. Let me see, can I make this bigger? Oh, much better. If you look on the right here, aluminum right there is +3. Hopefully you can see that. It's a little small on my end, so it might be small on your end too. Yeah, aluminum is +3, oxygen is -2. It just so happens sometimes the oxidation number overlaps with the charges. Okay. So when I was learning this, at this point, I'm like, why y'all using a new term, but it's the same thing? It's not always the same thing. And you see how it flips back and forth. So it's not the same thing. So for a while, I thought it was the same thing. I realized it wasn't as I got some questions wrong. Then I learned the rules because I was that one student who was trying to figure out if I don't have to learn the rule, why would I learn the rule? Right? That was me. Once again, there is hope. There is hope for you guys. Yeah. So from all this, we can see this is plus 3. Oh, remember I mentioned when you're writing oxidation number, you're writing it for each element, not the groups. So each element is plus 3, each aluminum, each oxygen is minus 2. Okay? Okay, where are we at? Oh, polyatomic ions. So we're using the same thing for polyatomic ions, right? And the polyatomic ions, we get to look at that and look at non-metal combinations. So I'm going to use sulfate. Yeah, we're dealing with polyatomic ions. So from the definition here, ions means it has a positive or negative charge. Polyatomic means many atoms. So you have a species that has many atoms, right? And they have a charge. So my example here that I'm going to work out is sulfate. Sulfate. Is this polyatomic? Yeah, there's sulfur and there's oxygen. Okay, and then we have our charge right here. So this fills that criteria. So the rules, according to what we're looking at, is the same. When you have the polyatomic, assign the nonmetal first, or the one that's surrounding. Okay, usually the one on the right. And then the one on the left has to adapt. So most of the time, this rule applies. Rule number 3, you're starting from right to left. Rule number 4 is different. Okay. Okay. So let's go from here. Okay. Oh, that's my boss. Okay. I'll read the email later. Okay, where was I? Sulfate. Sulfate. Let's see. Sulfate. So for sulfate, 2 minus. Once again, since I'm applying rule number 3, because rule number 3 applies here, I'm going to assign the oxidation number of the nonmetal first, and then assign the well, they're both nonmetal. Okay, the one that's surrounding first, right? The one on the right. Then the one on the left has to quote unquote adapt to what's going on. Okay, like we mentioned before with the overall compound, the overall oxidation number must equal charge, must equal, I should say here, overall charge. Overall charge. Okay, since my overall charge is -2, my overall oxidation has to equal -2. Okay, so now we're going to be doing the math right here. So I have sulfur, I have oxygen. Okay, for the sake of remembering how many we have, you can see you have only one sulfur here, and you have, I'll put 4 here for 4 oxygens, or we can leave that part out. You all know there's 4 oxygens, right? And the overall charge has to be -2. Okay, so in this formula of sulfate, I have 4 oxygens. So 1, 2, 3, 4. And I have 1 sulfur. This is 1 sulfur over here. Since I'm assigning oxygen first, each oxygen has to have the oxidation number based on the charge, which should be -2. So I'm going over here, periodic table, there it is, -2. So -2, -2, -2, -2, since we have 4 of them, right? So when we total this, we have a total of -8, right, from the oxygen alone. But we're told sulfur has to adapt to what oxygen is. So whatever sulfur is, when you add to oxygen, you get a total or an excess of -2. Okay. Now here you can approach it so many different ways. You can do it mathematically, you can do it visually, whatever works. Let me do the visual first and finish this story here. So since sulfur has to adapt to oxygen, oxygen brings in -8, sulfur has to bring in +6. So the total is -2, right? So this would be +6. So +6 -8 gives -2. Or if I want to be more visual, I can write it this way. positive, positive, positive. But this is communicating something else. So let me stick with the original because that's going to say something else, right? Just plus six. If I write three plus twos, it makes it sound as though we had three sulfur. We only had one sulfur. Okay. The mathematical way you can approach this same problem here is by saying it takes one sulfur plus four oxygens to equal a negative 2 oxidation number. The sulfur plus 4 oxygens. Each oxygen is what? Minus 2. Equal minus 2. You multiply this out and you get minus 8. Equal minus 2. So what must sulfur be? Plus 8 plus 8. This zeroes out. Sulfur equal plus 6. So if sulfur is plus 6 and then you have 4 oxygens each minus 2, you get a total of minus 2 overall. So you can use the math way to figure it out. You can use the conceptual way to figure it out. Pick a way that works for you, and that should work out. So if you're assigning, once again, you're right on top of the sulfur, that the sulfur is with the oxidation number of plus 6, oxygen minus 2. So once again, we go over this because it was covered in 1411, but many of you come to me, and I'm assuming you probably have forgotten. It's been a while, right? As I was told yesterday, we've slept since then. Okay. So our final rule is this one right here, rule 4A and 4B. 4A and 4B is one of those rare rules in chemistry where we're told something happens all the time. Okay. So in my journey of learning chemistry, a lot of the rules had exceptions. And I was fine with the rules. I hated the exceptions as a student because I was like, the exceptions always made things harder. Applying the rule, I was like, okay, I can do that. Then the exception, I was like, yeah, I was that student. So rule number four, 4A and 4B is a rule that you apply all the time. So these are the kind of rules I'm like, yes, all the time. So 4A and 4B deals with compounds. If you have a ionic compound with group 1A metal, the metal has an oxidation number of 1. Ah, okay. Let me write this better. I can do better. Number of 1. So what I mean by that is, say you're given KCl, sodium oxide, what else? Lithium, phosphide, okay? Because all of these ionic compounds where the metal is a group 1 metal, the oxidation number will be plus 1, plus 1, plus 1. But not only that, we're told we need to assign the oxidation number to the metal first. And then this time, the non-metal has to adapt. Okay? So when I learned this, I was like, yes, for switching it out. Okay? The same is true if you have a group 2A metal has an oxidation number of 2. Once again, and you want to once again assign this first. I know some things I'm writing, some things I'm saying it out. You kind of have to get it all, right? Once again, assign this first. Okay. So of course I gave you guys some summaries of my own experiences and what I did. But what I usually do is because rule number 3 and rule number 4 apply to compounds, I actually applied 4 first before 3. I know they said that the rules are written in order of priorities, but I had my own personal priorities because I was like, it's one thing to follow what they're saying, and it's something else to have real life experience, right? So I'm like, I think rule number 4A should be applied first. If it fails, then go to rule number 3. Okay. So once again, this one here, you have magnesium chloride. Magnesium is a group 2 metal, so it has to be assigned first, and it has to have a plus 2. Oops, what happened? It has to have a +2 oxidation number. Okay? And then chlorine will have to adapt. It'll be what? -1. Okay? So let's go ahead and make sure I've read over everything they have said over here. I know I wrote a lot. We went over this one here. Free elements have an oxidation number of 0. We went over that. Monatomic ions have an oxidation number that's, or oxidation state or number is the same thing, that is equal to their charges. We did that. The total sum of oxidation states of all atoms in the neutral compound is 0. We went over that, right? This is 3A, where you assign the element on the right first before the element on the left. They kind of consolidated stuff here. Skip over all the stuff I wrote. Go all the way down here to this rule where it says the sum of the oxidation states of all the atoms in polyatomic ions equal the charge of the ion. Okay? Once again, in this case, nitrate, assign oxygen first, the 3 oxygens first, then assign N. And then when you add the oxidation numbers, they should total -1, right? And so we've done that rule. Rule 4A applies to compounds where the metal is group 1 metal. Group 1 metals have an oxidation state of +1 in all their compounds, and you want to assign this first. It saves you a headache. Here, 4B, group 2 metals have an oxidation state of +2 in all their compounds. We love all, because this is rare in chemistry. In chemistry, there's always an exception, right? Always an exception. So they say in general. That means it's an exception. Okay, so we're going to be reviewing rules for assigning oxidation states in these compounds right here. But what I'll do is I'll actually do it for both of them, not just for some. I'll do, because I think over here they assign oxidation state for the nonmetals, but I'm like, but what if there's two? So we're reviewing the rules, right? So I'm going to look at this right here. Let me see if can I copy this? Copy. Okay. Oh, it showed up over. Okay. Okay. So what I'm going to do here, we're going to go to an assign oxidation states for this one here. I'm going to write it and then, of course, erase it. And we're just going to write the oxidation state on either side. For the carbon, I'll write it right here. For the fluorine right here. Okay? Okay. As I work on it, I'll put the work on the right-hand side. Okay? So the carbon will be on the left, the nitrogen on the right. I mean, the first element will be oxidation number on the left. Then the second element I'll put on the right because I'm trying to make use of the space I have. So starting with CF4. Since the whole compound does not have a charge, the overall compound does not have an oxidation state. But that's okay because we are assigning oxidation states for the elements in the compound. Okay? So starting with this one here, remember there's 4 fluorines. You want to assign this first, and this one here has to adapt. So we're going to have 1, 2, 3, 4, right? According to this formula right here. Each fluorine has to have a -1 oxidation number. It has to match the charge. So -1, -1, -1, -1. Correct? That means because of what fluorine brings into the table, carbon has to adapt. It's going to be +4 total to make the whole compound neutral. That means this carbon is going to be +4. So I'm going to write here +4 for each carbon, -1 for each fluorine. Okay? CH4. Okay, once again, let's start. 1, 2, 3, 4. So looking at this right here, hydrogen, each hydrogen is +1, correct? +1, +1, +1, +1. So since hydrogen totals +4, that means carbon has to adapt to, oops, I just realized, what did I do here? What did I do? Oh, no. Oh, my bad. Yeah, carbon has to adapt to hydrogen, so carbon will have to be -4 to make the whole compound neutral, correct? So each hydrogen is going to be +1. Each carbon will be -4 because we have one carbon. It's going to be 1 here, -4. Okay, that's what I'm saying. It's not necessarily charges, even though sometimes it is charges. We are following the rules. So moving on, we have CO2 next. With CO2, same thing. Each O is going to be -2, right, based on the charge. So -2, -2. We do have two O's, right? The O's together bring in -2 oxidation number. That means since we have one carbon, that one carbon has to be +4. Then overall, we get neutral, right? We get 0 overall. So this is going to be -2 for each oxygen, +4 for each carbon, and we're good to go. Okay, moving on. C, C, L, and of course we have four of these. So 1, 2, 3, 4. So it'll be -1, -1, -1, -1, -4, making this +4, right? So -1 for each chlorine, +4 for each carbon. You get that? You get the hang of things, right? Okay, CS2. Right here, each sulfur is -2, -2, -2, total -4. Each carbon has to be +4 for the whole thing to be neutral, right? -2 each sulfur, each carbon is +4. Okay, final one. Now I did add two more to class yesterday. Since I make things in the fly and I don't remember what I did, but let me try aluminum oxide. Then let me do sodium phosphide and magnesium oxide. How about that? So I added these and then we'll see. Get some more practice. So we'll do this here, just like I'm doing right here. Remember, these are the oxidation numbers for the elements. The one on the left, these are the first element in the compound. The one on the right is the second element in the compound. Okay, just in case you're wondering. First element, second element, because I'm trying to make use of the space I have. Okay, so for the NH3, assign the H first. So the H gets what? Over here. Just in case you've forgotten, positive. So +1, +1, +1, because we have three of them, right? And this is going to be +3. And then assign the N. Since we only have N, one N has to be -3. So this is going to be +3. This is going to be -3. Okay, we're doing good. And then the ones I added in, Al, you got two of these and then three oxygens. Okay, so back to this. Each oxygen has to be -2. So -2, -2, -2 to make -6. So whatever this is, it has a total +6, right? We have two of them, so it's going to be +3, +3. So each aluminum is +3, each oxygen is -2. So hopefully this is getting a little boring. If it's getting a little boring, that means you figured it out. If it's getting boring because you haven't figured it out, you're just checking out, that's not good. Please rewind and watch this again. Okay. Okay. So for the last two problems, I brought these in. Actually, I should start it here. When your first element is a metal, you have to ask yourself, does group 4 apply? If the first element is in group 1, one of these, metal, or group 2, metal, it can't be non-metal. So hydrogen does not apply. Either one of these, all the way down here. You have to assign the metal first, and for group 1 metal, it has to have an oxidation number of +1. Group 2 metal has to have an oxidation number of +2. Okay? So for the sodium, there's 3 here, and then the phosphorus or phosphide, there's this one over here. Each sodium has to be assigned oxidation number of +1. So we get +3 from these total. Since there's only one phosphorus, there has to be -3, meaning each phosphide is -3. I cannot speak right now. +1. You have to assign the sodium first because it's in group 1, and rule 4A says those gets assigned first. Get assigned first. Right? Okay. For magnesium, same thing. You have to assign magnesium first because it's in group 2. It has that special rule just for it. Magnesium in group 2 gets the designation, so it gets the oxidation number of +2. So oxygen has to adapt, and it's going to be -2. So -2 plus 2. The end. Okay? So if we're looking at this table right here, we answered all of this and then some, right? We did all the other ones, but we went through and answered all of this. So hopefully that makes sense. Please notice that the oxidation state of carbon adapts to what's going on. It's not necessarily constant. It changes depending on what you're looking at. Okay. Over here, once again, we're still going over this, right? Pretend you're not seeing what I'm doing right now. You probably aren't. You probably are. I don't know. But the goal is for us to remember the rules as we're going through this. So let's go through this together. Remember the rules. Okay. So this is an element by itself. So rule 1 says oxidation number is 0. This is rule 2. It's a monatomic ion. Oxidation number +1. Here we have two elements. Lithium is in group 1. You want to assign this first. +1. That means fluoride will be -1, right? Oxidation number. So I'm going to put them in circles to be consistent. With carbon and 2 oxygens, carbon dioxide, each oxygen is -2, meaning the carbon has to be +4. Okay? So right now I'm looking at this. I'm running out of space. I'm going to do the same thing I did before, which is assign these here. So 0, +1 for potassium, +1 for lithium, -1 for fluoride, because I'm already running out of the room and I need the room to work things out. Okay, so for carbon dioxide, oh, that's the one I just worked out, right? -2 and then +4. Okay, so moving on from here, SO42 minus. We worked on that before, didn't we? What we did work on was NO3 minus. So let me work on that one instead, because we already worked on this before. So I'm going to work on NO3 minus, because I didn't get a chance to work on that. NO3 minus. So each nitrogen, oh, sorry, we're doing the oxygen first, right? Each oxygen is -2. So -2, oxidation state, and -2 oxidation state, -6. Overall is -1. So whatever this has to be based on what we're working with here, this has to be +5, right? +5. So if I put nitrate here, the N has to be +5. Then each O has to be -2 for this to work out. Oops. See, that's out of the way. Okay. Yeah. The next one here, we're looking at sodium peroxide, like hydrogen peroxide. Since we have sodium first and then oxygen, each sodium has to be assigned first, because rule number 4A says if your metal comes from group 1A, it gets assigned first. Then the non-metal has to adapt. So each sodium is +1, +1, right? And we have 2 oxygens. The sodium have to total 2. The oxygen have to total 2. +2, -2. That means, okay, each oxygen has to be what? -1. We spent some time discussing this in lecture yesterday. I was so tired yesterday. It wasn't even fun. Like, I was really tired. But we spent a lot of time discussing this in lecture yesterday, right? The oxygen cannot be -2, because if oxygen is -2, then we end up with -4, right? And this will not be neutral. This would be NaO2. I mean Na2O2 -2. So oxygen has to adapt. Now remember, these oxidation numbers are not charges. They are numbers to help us follow along to determine what's being oxidized and what's being reduced. Okay? Each oxygen here will be -1. This would be +1 for each sodium. Moving on, let's see what happens here. Do we have a group 1 metal? No, we don't. So assign the hydrogen first. Each hydrogen has to be what? We have H4, C, plus 1, plus 1, plus 1, plus 1. So ends up being what? Plus 4. Each carbon has to be minus 4. So we have plus 1 for each hydrogen, minus 4 for each carbon. Then finally, when we're moving on and looking at this scenario here, ooh, my hands are lingering over this pad and I'm just messing things up. Hold on. Okay. Ah, undo right here. Okay. Since sodium hydride, you have that group 1 metal that has to be assigned first. This would be plus 1, and this has to be minus 1 to adapt, right? Because this has to be total of minus 1, this has to be total of plus 1. So sodium will be plus 1, hydrogen will be minus 1. But in the previous combination, hydrogen was plus 1. That's why you can't just memorize these. You have to know the rules and know how to apply them, right? Okay, let me see. Okay. If you have any question, Ruby, feel free to ask. It's warm in here. Okay, so we're gonna move on. Right, we talked quite a bit yesterday. And then we talked about, once you learn all that, then you can apply that to figuring out what's oxidation, what is reduction, what is the agent, and then move on from here, right? So looking at this, we're told oxidation occurs when an atom's oxidation state increases due to the reaction. So this is why we learn how to assign the numbers. The numbers tell us how to identify if an atom is undergoing oxidation or if it's undergoing reduction. Reduction occurs when an atom's oxidation state or number decreases during the reaction. The redox reaction is split into two separate half reactions: oxidation reaction, reduction reaction. Okay, so let's look at this chemical reaction here and tell what's oxidation, what's reduction. Now, one way you can tell real quick by the chemical reaction is oxidation or reduction is by looking and seeing if the oxygen is being added or not. Okay, give me just a moment, Ruby. I heard a thud. I think I can get away from this page here, right? I think I'm good. Get away from that page. Y'all excuse the mess. Okay. Oh no. But can you hear me though? I hope you can hear me. Oh, okay, okay. Because if you cannot hear me, then this whole recording did not work. I mean, it shows on my end here that the mic is working, but I'm a little paranoid about this because I've done a whole recording and I forgot to turn the audio on. So, time is premium. Where's my page? Okay, as long as you can hear me, we're good. We're good. Whew. Okay, so let's go through and apply the rules here and then we'll go from here. So with the rules, once again, find the easiest one, the element by itself. Right here, this one has an oxidation number of 0. Right? Rule number 1 said you find an element by itself. If it's a non-metal and it's one of the Brinkerhoff elements, it has to be like, the element sub 2 because it's diatomic. Assign the oxidation number of 0. Okay? We have the 3 other compounds. Since none of them have a metal, we'll start from the right to the left, correct? So we know each hydrogen here is plus 1 because you assign the hydrogen first based on the charge. So 4 plus 1 make a total of what? Plus 4, correct? Because it's going to be plus 1, 4 times. Let me not skimp on this. Plus 1, plus 1, plus 1, plus 1, total of plus 4. So the carbon has to be minus 4, right? So the carbon has to be minus 4. Okay. Yeah, thank you. Now you're writing the oxidation number for only one element. It took me yeah, I kind of had to do a mental switch on that one to really understand it. Now I can do the mental switch very easily, but in the beginning for me, I have a mind that fixates. If you have a mind like that, then you understand what I'm talking about. And your mind is stuck on a process you learned before, and it's trying to force that process here. And the book is saying, no, don't do that. And so you have to adapt your mind, and that's what studying does. It helps you kind of switch. Okay, here we'll go with the carbon. Sorry, we're going with the oxygen first, right? From right to left. The oxygen each is minus 2 based on the charge. That's the oxidation number also. So total here we get -4. So in this case, carbon has to adapt and be +4. So here we have +4 with carbon, -2 with each oxygen, and we're good, right? This is too big. Let me write a little bit smaller. So each oxygen is 0 here. And on the product side, for I'll just leave it like that. For each oxygen here, we have one oxygen that's -2, and we have two hydrogens. So each hydrogen has to be +1, +1. So in the end, I have +1 here for each hydrogen, and each oxygen is -2, correct? So now I do the overall assessment. Now that I've assigned these numbers, now I'm examining these overall. Okay, we have a carbon on the left, a carbon on the right. Do we see a change? Yes. Carbon goes from -4 to +4. -4 plus 4, think number line, right? You go from some number to 0 to the positive. So you got negative on the left, positive on the right. So we'll say -4, -2, -3, -2, -1. I don't know why I can't count. To 0 plus 1 plus 2 plus 3 plus 4. Any transformation that leads from the more negative side to the more positive side is oxidation. If it leads to the opposite direction, it's reduction. Okay, I'm doing a lot, yeah, but that's what I mean. Okay, so if you're going from -4 to +4, the direction is towards the right. That's going to be oxidation, and the oxidation number is increasing, right? So oxidation. Now, are all the elements being oxidized? No, only carbon is being oxidized. Okay, only carbon is being oxidized, because look at hydrogen. Hydrogen is going from +1 to +1. That's not changing. So only carbon is undergoing oxidation. Okay, so we judge it by element, even though it's an element in the compound. Okay, what about oxygen here? Oxygen goes from 0 to -2. So if you look at this, the oxidation number is decreasing in oxygen, decreasing, aka reducing. So oxygen is undergoing reduction. And so I mentioned this yesterday, that I learned this by doing a lot of problems, trial and error, that in per one chemical reaction, you only have one oxidation and one reduction. So every chemical reaction has that's a redox reaction, is redox. One red for one ox. We don't have red red. There's no red red or read read. This doesn't exist. And there's no ox ox. Doesn't exist either. You don't have multiple reads in one reaction, meaning that when you've worked hard to identify the one element being reduced, that's the only element being reduced. All you have to figure out is the one that's being oxidized. Once you find them both, that's it. There's nothing else to figure out. Everything else will not be changing, right? So there's only one reduction, and then its corresponding oxidation. And you don't have two reductions in one reaction or two oxidations in one reaction. Okay? Just in case you're wondering. Because when I was a student, I was like, ooh, how many can I find in one? It was just one of each. Okay, so we're going to be learning about the agent, right? Yep, there it is. And I'm going to use the same example. Or I'll just use this one down here to describe the agents. So for this one here, to give you guys more examples, we're going to deal with sodium metal reacting with chlorine gas. Sodium metal, so it's going to be a solid. And when they combine, they form table salt, sodium chloride. Now, do they have it as a solid here? Yeah. I'll leave it in this form as a solid. Okay, so once again, let's go through and assign oxidation numbers. Since these two are free by themselves, sodium is going to be 0, chlorine is going to be 0. Okay, in the compound, we're either applying rule 3 or rule 4. Since we recognize sodium as a group 1 metal, forget rule 3. Let's go straight to rule 4a. 4a says if you have a group 1 metal, then assign the metal first. It has to be +1. Then the other element has to adapt to the metal. So this would be -1, which is so much easier than doing the other math that we're doing before, right? Or maybe it's the same. I don't know. To me, it's simple. Okay, now that we're done with that, we're being asked to first of all figure out what's being oxidized, what's being reduced, then assign the agents. And so I mentioned in class, if I were famous, if I had this amazing talent and I was famous, right? If this is not happening, but hypothetically, and I hired an agent, what will the agent be doing for me? And then somebody mentioned, well, the agent will be getting you jobs or stuff like that. I'm like, yeah, the agent will make it possible for me to do what I do, right? The agent is the one that facilitates, makes it possible, creates an environment where I can do what I want to do. Okay. So using that understanding of what an agent does, let's go ahead and see how the chemicals here can be agents of each other, almost like advocates to help the other element do what it's going to do. So let's see what happens to sodium first. Sodium goes from zero oxidation state to +1. So sodium, having a greater oxidation state in the chemical reaction, is being oxidized, right? Because it's going from 0 to +1. And then chlorine, in this case, is going from 0 to -1. So remember the number line, right? Negative to 0, 0 to positive. If you're going from 0 to +1, that's oxidation because you're going towards the right, more positive. If you're going from 0 to -1, that's reduction because you're going more to the left. So in this case, this would be more reduction because you're going left, and then reduction. Oxidation because you're going right in the number line. That's how I look at it. Sodium is oxidized, and then here, chlorine is reduced. Okay. The other example I used in class yesterday, I think it helps for me to have done this in class yesterday. The other example I used was to talk about, the agent is when I was growing up, my mom would be like, clean your room. And I'll be out there distracted, playing, doing whatever it was. And as soon as she showed up, she opened the door. Her presence made me work fast. Whatever I was doing wasn't important anymore. As soon as she showed up, it changed my behavior, right? And so I think about that this way, that if you have chlorine by itself is not by itself, will not be undergoing reduction. But once you bring in sodium, sodium's presence causes chlorine to change and get reduced. Sodium by itself will not be oxidized, it will just be there doing its thing. But once you bring in chlorine, sodium becomes oxidized. So chlorine is helping sodium to be oxidized, while sodium is helping chlorine to be reduced. So they're helping each other, right? They have some kind of codependent relationship. So, because of what they do to each other, we'll say here that sodium is actually a reducing agent because it causes reduction in chlorine when it shows up to the reaction. Okay? And then chlorine is reduced, but at the same time, it's an oxidizing agent. Kind of not really the enforcer, but the encourager, right? So its presence causes the other element to respond by doing what it was supposed to do or what it was meant to do. So sodium makes chlorine reduce. And then chlorine makes sodium oxidize. So they're agents of each other to facilitate that reaction. Okay? And so the formal definition here, once again, oxidation and reduction mostly occur simultaneously. If an atom loses an electron, another atom must take the electron. Like I said, it's a yin and yang relationship to make sure that charges are conserved. Okay, you can't just have random electrons being produced in nature without something else taking in those electrons. The reactant that reduces an element in another reactant is called the reducing agent. The reducing agent contains the element that is oxidized. The reactant that oxidizes an element in another reactant is called oxidizing agent. The oxidizing agent contains the element that's being reduced. So we've seen that in here, right? Sodium is oxidized, chlorine is reduced. Sodium is the reducing agent, chlorine is the oxidizing agent. Okay, then we moved on right here. So here we're seeing more, I'm trying to write this out without having all the stuff on there. Give me just a moment, let me write this out. I know. Instead of copying this out, I'm just gonna add this here. And then we'll get to the part where I got stuck yesterday. Man, my brain was fried. I could not see stuff on the board. I mean, I could see it. I just wasn't comprehending it. When I get so tired, my processor in the head just shuts down. I can look at stuff, I just cannot process it through. And I was not processing this, not this one, the last one that we stopped at in lecture yesterday. I was not processing it. Like I could see it, I just could not process the material. Anyway, let's go ahead and look at this right here. FeMnO4 minus plus 4H plus to give us Fe3 plus MnO2. Let me decrease this right here. Decrease this. Plus 2H2O. Okay, so we have this here. Now, for this question, they're saying find what elements is oxidized, was reduced, determine the oxidizing agent and the reducing agent. Okay, we can do that. Having this right here, let me start with the easy target. The easy one is iron. Oxidation number 0. That's rule number 1. Find the element by itself, the loner element with no charge around it. Oxidation number for that one is going to be 0. This is the next easy one. Oxidation number plus 1. Now, even though you have the stoichiometry coefficient, we want to know what's going on with one element, not the group. Remember, we're not assigning to the group, we're assigning per element. So plus 1. Iron. This one iron by itself is plus 3, right? Based on rule number 2. The oxidation number is equal to the charge of the monoatomic ion. Okay, now we have compounds here. Let me do water first because it's a little bit easier. With water, I assign oxygen first. It has to be minus 2 equal to the charge. And since you have one oxygen and 2 hydrogens, each must be plus 1, right? So plus 1. And the more you do these, the more you get used to it because the oxidation numbers will be the same if the compound is the same. Even if it's a different question, it's the same value, right? As long as you have the same 2 elements in the compound. It could be 3 also, okay? Now let's deal with MnO2.
So that
MnO2. Sorry, yeah?
so the 2 on the H2O, the first 2, the one that we usually use like for stoichiometry, that's not going to get dispersed into like hydrogen and
No.
oxygen? Okay.
No, it won't because we're assigning oxidation numbers for one element,
Okay.
regardless of how much it takes to balance the equation, right? That's why even when it's like H2, we don't say plus 2 because we're only assigning it for one element. Right.
Okay.
Yeah. Yeah, thank you for that question because that helps to clarify that, right? Okay. So right. Now we have a metal and a non-metal. And the metal is not group 1 or group 2, so we won't assign that first. We'll assign the non-metal first and then assign the metal. So the non-metal is going to be minus 2. Each oxygen here is minus 2 to give us a total of what? Minus 4. That means manganese has to be plus 4 because we only have 1. So this is going to be minus 2 for each oxygen, not the group together. And that means manganese has to each be plus 4. Okay, so I'm kind of slowing it down a little bit with those ones because they're a little bit more complicated. And then when you get the hang of this, y'all, because I saw Austin doing it yesterday, it's the same numbers, but you have to do a bunch of them to kind of get used to them, right? Where you can kind of just skim through and get the answers. Here we have a charge, and I left this one here for last. So our overall has to be equal to minus 1. We have 4 oxygens, right? And then we have manganese again. Each oxygen is going to be minus 2, minus 2. We assign those first because manganese is not one of those special metals. It's not group 1 or group 2. It's not magnesium. Don't confuse Mn with Mg. Okay, total we have here minus 8. Whatever Mn is, when you add it to minus 8, you must equal minus 1. So doing the math, plus 8, we end up with plus 7. So Mn by itself has to be plus 7. So over here, Mn has to be plus 7, right? And then this one here has to be, each has to be minus 2. So the overall can be minus 1. Okay, now that we've done all this, remember all of this math, all of this stuff is a means to an end. We're still trying to identify what's being oxidized, what's being reduced. Now I can look. Iron goes from 0 to +3. Oh, that's getting bigger. We're going towards the right. That's definitely being oxidized, right? And they asked us to find the agent. Whatever is being oxidized is also the reducing agent. Okay. Now let's see. Next one, manganese. Mn is +7, +4. Yeah, right there. So this, since the oxidation number is reducing, then Mn, not O, just Mn is the reducing agent. Ah, sorry, it's being reduced. What was I saying? I was just looking at the other word and copying it, and I realized, what am I doing? Reduce. And it's the oxidizing agent. Okay. Now, you can check if you want to look at the other ones. Oxygen is -2 to -2, no change to -2 here. Hydrogen is +1 to +1, no change. So the only ones that are changing are iron and manganese in the whole reaction. Iron is being oxidized, so it's a reducing agent. Manganese is being reduced, so it's the oxidizing agent. Okay, so it's not as bad as it seems. It's just kind of tedious. You have to go through all that math just to make that conclusion. But that is it for that one. And then this one was the one I need to learn the process they're using here, because my student Sally, she got this down. The process they use here, the way I do it is different from the way they do it, because that's kind of the old school way. But this is where we are balancing the redox reaction. So this is a step up from what we did in 1411. In 1411, we're balancing regular reactions. Now we're balancing redox reactions. So we want to go in order, right? And these steps do matter when you're working on this. You want to make sure you go in the order. First thing you want to do is assign oxidation states by determining the element being oxidized and the element being reduced. Write the oxidation and reduction half reactions. Okay? So we're going in this order. And what I'm going to do here is I'm going to take a screenshot of this just so I can have it next to me, because I'm trying to learn it the way that they're doing here, because I think it's easier if you're following the directions they have here versus me writing new directions. But I'm not familiar with this process here. But I think it's just more, it's easier for you if I follow the rules, if the rules actually are easy to follow. So I'm going to do that. Okay, follow the rules. Okay, so if you're going along with me, you want to take a screenshot of what we're doing right now so you can follow along, because when I have the page open, we will not be looking at this. We're going to go in order though, based on what's going on. So going in order, we're going to try to balance this part here first. So I'm going to tell you, with these type of reactions, the easiest ones to work with are the ones where there is no oxygen or hydrogen at all in the equation. Can you imagine? Oxygens and hydrogens make balancing the equation more difficult. Not in Gen Chem 1, but for Gen Chem 2 redox reactions, yes, it does make it more difficult. So I'm going to copy this over, and this should be straightforward because there is no oxygen or hydrogen. And I'll show you why. Okay. So in balancing this out, we have, let's see, the rule says assign oxidation states by determining the element oxidized and the element reduced. So let's go ahead and use the rules to assign oxidation states, starting with this one here. Aluminum is a solid, so it's going to be 0. Aluminum here, let's see, oh, this is copper is a solid, so it's going to be 0. There's no charge around it, right? Copper here is an ion, so it's going to be +2. Copper here, I'm sorry, aluminum here is an ion, it's going to be +3. Okay, that was pretty straightforward. This is the easiest you will see. No math, just a sign, right? Okay, now we want to see. I can't use rule number 3 just yet, but it says write the oxidation and reduction half reaction. Okay, so from 0 to +3, that's oxidation, right? I write here oxidation. And from +2 to 0, that's definitely reducing, so reduction. And this is copper that's been reduced. This is aluminum that's being oxidized. So the half reaction will be Al solid to give us Al3 plus aqueous. Next one is copper 2 plus aqueous. to give us copper solid. Okay? So rule number 3 will not apply here because rule number 3, well, I shouldn't say it will not apply here. Let me apply it as much as I can. It says the first thing is balancing your reaction by mass. You're balancing the atoms. On the left, I have one aluminum. On the right, I have one aluminum. On the left, I have one copper. On the right, I have one copper. So the hydrogen, non-oxygen elements are balanced. So rule number 3, I'm going to paraphrase it, is saying that we want to balance the non-oxygen, non-hydrogen first. Neither of these is oxygen or hydrogen. And when I check both sides, I have equal amounts as far as the atoms are concerned. I'm not balancing charges just yet. Okay? Rule number 4 says when all of this is done, you can now go ahead and include electrons. So you want to go ahead and include electrons. So when I look at this side right here, I'm gonna try to use. Let me try to separate these a little bit more. I'm gonna use visual to illustrate what I'm doing. On the left of the balanced equation, I have 0 charge, right? There's no charge here. On the right, I have 3 positives. Okay. The only way to balance the reaction is to make sure the overall charge on the left matches the charges on the right. We can balance the equation by adding electrons only. So we are adding electrons to balance equation. That's the only way we can balance the charges. We cannot subtract electrons or add something positive. We can only add electrons to balance the equation. Since the left side has 0, our goal is to make the right side 0 also, right? We tend to add electrons to the more positive side. So I should say add electrons to more positive side. I forgot to do something, okay? I forgot to say here, this is oxidation. One of the definitions we said of oxidation is you have electrons on the product side. So when we're adding electrons, they should go on the product side. This other one here is going to be the reduction. One of the definitions of reduction is you have electrons on the reactant side. But just to kind of make sure you understand this, we add electrons to the relatively more positive side. So I'm going to add an electron here, an electron here, an electron here to neutralize the right side to make it match the left side. Okay? I have to add one negative for each positive to make it overall 0. So you see this is neutralized here, here, here. So in order to make the right side match the left side, I had to add 3 electrons. So you put plus 3 electrons here. So as far as the rule is concerned, that half reaction is balanced. On this left side here, I have to, once again, I have no charge on the reduction reaction. I have no charge on the right side, but I have a positive 2 on the left side. I have to make the left side match the right side. The right side is 0. It's neutral, 0. I need to make the left side also neutral, 0. I do so by adding charges, negative here, negative here. Okay? Since it takes me 2 electrons to make the left side neutral like the right side, I'm going to add here plus 2 electrons. In the reduction reaction, we tend to have electrons as reactants. Okay? Now I'm trying to see what the rules say. Number 5 says balance half reaction. We want to balance the half reaction by adjusting the charges. Okay? These pictures were a means to an end. So just to kind of clean up things visually, let me go ahead and erase those. If you want to see them again, please just rewind. I'm at a state right now where I get very easily visually distracted. So I'm just doing that for your sake, but for my sake also. Okay, so we have this right here. We're trying to make sure the number of electrons made in the oxidation reaction will all be consumed in the reduction reaction. Remember, these reactions are codependent on each other. They depend on each other. The oxidation reaction depends on the reduction reaction. It depends on the number of electrons made in the oxidation reaction. So we have to make sure all the electrons made in the oxidation reaction are used up by the reduction reaction to have a complete, cycle. To do that, we're going to actually multiply this whole reaction by 2. To make, since we have 3 electrons in one reaction and 2 in the other, our goal is to make them both 6. We'll multiply the second one by 3. Okay, so when you open the parentheses here, you have 2Als, 2Al3 plus 6 electrons, right? So the oxidation half reaction is now balanced. Let's look at the reduction half reaction and see that's balanced. Open the parentheses here, we have 3Cu2 plus aqueous plus 6 electrons to give us 3Cus. Okay? Now that we have these two, we're going to add this reaction to this reaction. So once again, for visual purposes, let me go ahead and erase this right now. If you want to see it, feel free to rewind. I know the luxuries of technology, right? So if you want to go back and see the other one, feel free to rewind. So I'm going to add this top reaction to this. As I'm adding them, you're free to cancel out the electrons because we have the same number of electrons here. Remember, when you're trying to add two chemical reactions, if you have the same chemical species on both sides of the equation, you can consolidate, bring them together, right? So I'm canceling out the electrons here and here. So what I end up with is 2Als plus 3Cu2 plus aqueous to give me 2Al3 plus. I'm bringing down all the reactions on the same side and all the products on the same side, 3Cu solid. Okay, now you want to make sure the charges matches, right? The atoms have to match. You have 2Als here, 2Als here, 3Cu here, 3Cu here. 3 times 2 plus is 6 plus. 2 times 3 plus is 6 plus. So this balances because the atoms balance and then the charge balances, right? So you want to make sure that you go through and you see that. The atoms have to balance, the charge has to balance, and that tells you you're doing the right process. So this right here is balanced. It's hard to tell if this is balanced in acid or base, but we're going to be balancing in acid and balancing in base as we go through the rules in more detail. So that's our first one. Over here, they're saying balancing a redox reaction in an acidic environment. So I'm going to be working on this second one. And this second one here, and I did work on these additional ones in class yesterday, which explains why I was so tired. Yeah, these kind of questions, they're fun, but it's like when they're mentally tasking. So they do require, a lot of mental energy. Overall, though, I do think they're fun. It's just when you're tired, it's kind of hard to push through that fatigue. But if that's the case with you, go ahead, work through it, and then come back and look at it again the next day. Hopefully it gets better. So we're going to be balancing this equation. This is a redox equation. We're going to be balancing it using the redox rules. So before the little break I took, I wanted to make sure I had the rules next to me. So I'm going through the rules as I'm following it. We can see both sides of the screen. So I'm going to have this here so I can look at it. Okay. First thing it says here, assign oxidation states by determining the element oxidized and the element reduced. So let's go ahead and assign oxidation states. This is balancing redox reactions, right? And usually the default balancing is in acids. So balancing redox reactions in acids. So at least for this reaction here, we are balancing it in acids. So hopefully you're able to see that. Okay, I'm going to go through and do number 1. I'm going to assign oxidation states by determining the element being oxidized and the element being reduced. I don't normally go this way. The way I work it right here is different based on how I was taught when I was in school, but I'm trying to learn this way, so hopefully you can see the rules outlined, okay? So I'm going to start with the easiest formula to assign, and that will be for the monatomic ions. This is going to be +2 consistent with the charge, +3 consistent with the rule number 2, right, for monatomic ion, and then this is going to be +2. This is going to be rule number 3b. You don't have to remember the order of the rule, but that's the rule that talks about assigning oxidation numbers of polyatomic ions. So you want to do the nonmetal first, and then the metal second, or the central atom second. So we have 4 oxygens. Each of them is -2. And the overall charge must be -1. making Mn plus 7. So if you take plus 7 and subtract 8, you get minus 1. So this is going to be plus 7. This is going to be minus 2 each. And so this is what we're working with here. Okay, the next thing we're looking at, oops, this is kind of out of frame there. The next thing we're looking at is number 2, right oxidation and reduction half reaction. So oxidation and reduction half reaction, we're doing this right here, and then this right here. Fe is oxidized, right here, OX for oxidation. This one here is being reduced, as RAD for reduction. If you look at the numbers up here, it goes from plus 2 to plus 3. When you have an increase in oxidation number, that is oxidation. When you have a decrease in oxidation number, that is reduction. Mn is going from plus 7 to plus 2. Okay? So we can see over here when you separate this is Fe2 plus AQ to give us Fe3 plus AQ. This is oxidation. MnO4 minus AQ to give us Mn2 plus AQ. This is reduction. Okay, so I've done step number 2. Check. Step number 3 says balance half reactions by mass. So look at the elements. So first balance elements other than hydrogen and oxygen. Look at the non-hydrogen and non-oxygen elements. That will be Fe, Fe. That's balanced. We have the same number of Fe on either side. The next one is look at Mn. Mn and Mn. You have the same number of Mn's on both sides, right? And so the 3A is done. Both Fe's and both Mn's are balanced. 3B, we start by balancing oxygen first on both sides, oxidation and reduction. Then you go ahead and balance hydrogen, right? So balance oxygen first. We have 4 oxygens here and we have none on the right. Add water where oxygen is needed. So I'm going to add 4 waters because the rule is 1 water for every oxygen. Okay? But by doing that, you see right here, I have actually introduced 8 hydrogens. So I'm going to add 8 hydrogens here, 8 H pluses, AQ, because it says in rule number 3C, add H plus where hydrogen is needed. And this is a way of balancing. So once again, we're following the rules. For reaction done in base, balance an acid first, neutralize H plus by adding moles of OH to both sides of the equation. So it should say more, or equal moles of OH to both sides of the equation, okay? So I'm able to follow rules better when I've had a little bit of rest, and I've had a little bit more rest than yesterday. Yesterday I was just burned out. I'm still burned out today, but a little bit better. Okay, so we are balancing an acid. So for right now, we'll skip rule number D and we'll skip rule number E for right now. Okay. Then let's go ahead and include electrons. So including electrons, you want to check and see what charges you have on both sides. So real quick, I do have 3 positive charges here. So it'd be like plus 1, 2, 3 on the right side, correct? Of the oxidation reaction. On the left side, I have 1, 2. I want the left side to match the right side. And the rule is you balance electrons by adding electrons to the side that's more positive. This side, on the right side of the oxidation reaction, is more positive because it's one more positive sign. We want to get rid of that, and the only way to get rid of it is to add an electron. So I'm going to add an electron here. That will be negative. That way, this neutralizes that. If I add 1 electron, what I have in excess is now 2 positive excesses on the excess on the right side, and then 2 positive on the left side. So now they're evenly matched, right? 2 positive on the right, 2 positive on the left. So that half reaction is balanced. I'm going to put an electron here to show how the half reaction is balanced. On the second one here, I have a negative, and then here I have 1, 2, 3, 4, 5, 6, 7, 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 positive and then 1 negative. So looking at this right here, essentially this neutralizes this. So technically I have 7 positive excess on the left side. On the right side, I have 2 positive. 1, 2. As before, we want the left side to match the right side. Well, the rules say we can't bring in positive charge, but we can add negative electrons to the more positive side to make it more neutral, right? Or less positive. So I'm going to add in the number of electrons required on the left side of the reaction to make it only have two positives. So I'm going to add here negative, 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 negative. That's it, right? I need this here to match that. So I added 1, 2, 3, 4, 5. That means add 5 electrons on the left side to make the charges balance. By doing this right now, my charges are balanced, and then, of course, my atoms are balanced, right? And then the next thing says here, balance half reaction. Balance half reactions by adjusting electrons. Okay, so we're going to be doing that. This is a means to an end. Adjust half electrons, or I guess adjust electrons of the half reaction. So I'm going to do that right here. I want this to match this. So multiply this whole reaction here by 5. Okay, I'm not going to rewrite it. I'm just going to use it right here. So we're going to have 5 Fe 5 5. Okay, in doing so, look at that. Now our electrons match. This one here matches this. Okay, it's very important that the electrons match, like I mentioned before, because oxidation reduction reactions feed into each other, with oxidation being the electron maker or the electron producer, and then reduction being the electron consumer. So the oxidation feeds into the reduction, right? And then the cycle continues like that. They kind of sustain each other, yin and yang relationship. Okay, having this, now we can add the two half reactions, cancel out the electrons, and then we get the overall reaction. Okay, so number 6 is add half reactions. Check by counting atoms and total charge. Right. So I'm going to consolidate all the reactants together, right? 5Fe2 plus AQ plus MnO4 minus AQ plus 8H plus AQ. These are the aqueous reactants. And then the products, 5Fe3 plus AQ plus Mn2 plus AQ plus 4H2O. This is my overall reaction balanced in acid. How can I tell it's an acid, not in base? Because you see an 8H plus here. H plus tells you it is balanced in acid, BIA. That's just the thing I came up with. But it's balanced in acid. So we have done what the acids to do, which was balance the redox reaction in acid. I want to do another one that's on here. I saw it somewhere here. We had already worked this one out, right? This one here, I don't think I've ever been, and I usually don't do the 4 practice one, so I've never actually done this one here, but let me see if I can follow the rules. Because once again, remember, I'm learning how to do it their way, which is different from what I'm normally used to doing. So it's like if I'm tired, it's hard for me to learn new things, but I'm forcing myself to learn it because something about building pathways of learning in your brain or something like that. If you challenge your brain to learn new things all the time, it forces your brain to be flexible, right? To learn new things. The less you learn, the more rigid your brain becomes, and then it's hard for you to learn new things. So yeah, I'm trying to force myself. Even if I mess up, it's okay. It's part of the journey. Okay, paste image. The journey of flexibility, right? Forming those learning pathways. Anyway, that's what research says. So I'm trying to see this out. Okay. Wow, this is a different one. Like I said, I've never done this before, but we can do it. Let's see. Once again, following the rules. If I tell you guys to follow the rules, can I follow the rules? We'll see. Number 1, assign oxidation states by determining the elements oxidized and the elements reduced. Number 1, right? That's rule number 1 over here. So I'm going to assign oxidation states. +1, this is 0, this is 0. Oh, this is it's not that bad. And then Cr +2. Okay, so this is obviously reduced, right? Because the number line goes from 0 to positive, then negative like this. When you're going from positive to 0, that is a reduction. When you're going this way, that's going to be an oxidation. So from 0 to +2 is oxidation. So this one here, chromium, is being oxidized. Was it balancing an acid? Yeah. We're balancing an acid. So this is going to be oxidized. This is going to be reduced. Okay? This may not be as bad as I thought it's going to be. Let's see how it plays out though. Okay, so step number 1 done. Step number 2, write oxidation and reduction half reactions. I like doing my oxidation first, so I'm going to write Cr solid to give us Cr2 plus aqueous. The second one here is H plus aqueous to give us H2 gas. Okay, let's go ahead and work it out from here. So what do we have here? Oh, rule number 3, balance half reactions by mass. So check to make sure the non-hydrogen, non-oxygens are balanced first. Chromium is balanced. Hydrogen is not balanced. I'm going to double this here. Okay. Next one, add water where oxygen is needed. There's no oxygen needed here, so we can skip over that. Next one, add hydrogen where hydrogen is needed. Let's see. Do we need a hydrogen here? No, hydrogen is actually balanced. So next one. For reaction done in base. No, we're doing this in acid, so I can skip D. D is for reaction done in base. And then finally E, we consolidate. There's no consolidation needed here because we didn't really add H or OH and water, right? Finally, number 4, include electrons. So to include electrons here, I'm going to add electrons to the positive side. This is my oxidation side. This is my reduction side. Add electrons to the positive side. This is plus 2 already. This the left side is neutral, having no charge. So I need 2 electrons here. So I'm going to add 2 electrons, right? On this picture down here, this has got 2 positives. The right side has no charge. I need to add 2 negatives here to make it neutral. Oh, this question is not that bad at all. It just looks different, that's all. We don't even have to do step number 5 of adjust the electron because the electrons essentially do match. So here I have CRS plus 2H plus to give me CR2 plus AQ plus H2 gas. And this right here is balance. Okay. The reactions that don't have oxygen in them tend to go a lot quicker. So when you check here, you have 1 chromium, 1 chromium, 2 hydrogens, 2 hydrogens. The overall charge, you have 2 plus here, here we have 2 plus. So really, this is balanced in atoms and is balanced in charge. They do say check. And I have a bad habit. When I get very tired, I just take shortcuts. I don't mean to. I just, my mind becomes so fatigued that I'm just like, I want it to be done. So I'm just taking shortcuts, right? But I'm not doing that right now. I had a little bit of lunch, so that helps. The next one I'm going to be working on is this one here. Oh, I already worked on this one here, so I can actually delete this because I'm done with this. Yeah, let me delete this one here. How do I delete this? Or just paste the next one here. Okay, hold on. Let me copy this. Copy. Ignore that part. And then paste. So we are balancing this, but we're balancing this in what? Oh, in basic solution. So now we're going to be working on what they show. We have to do this part here, 3D and 3E. Okay, we can do this, y'all. When I say we, I mean I. Okay, start with the rules. The first rule says assign oxidation states for each element within the compound. So oxidation states for this one here, the easiest one, -1. This one here is 0, is the free elements. Each oxygen here is -2. Since we have 2 of them, it makes -4. We have 1 manganese, that should be +4, right? Each oxygen here is -2, making it 4 times 4 -8. That means manganese has to be +7. I think I assigned everything. If you look at I minus to I naught, you go from negative to 0 to positive. From negative to 0 is going to the right, so that's going to be oxidation. So this should be oxidation. By default, manganese is going to be reduction. Plus, you can tell how the oxidation number decreases. This is going to be reduction right here. Okay. Okay. Rule number two, right oxidation reduction half reaction. Okay. So we know on one step, I minus aqueous becomes I2 aqueous. In the other step, we have MnO4 minus aqueous, and this becomes MnO2 solid. This is the oxidation, and this is the reduction. Okay? So rule number three says balance half reactions by mass. Okay, I is not balanced because you have one on the left, you have two on the right. So put a two here. Okay. Mn is balanced. Mn, we have the same number. One Mn on the left, one Mn on the right. But if you look at the, so sorry, that takes care of rule number 3A. Rule number 3B says you want to look at the oxygen, and where you're deficient in oxygen, add water for every oxygen needed. So let me erase this. This is MnO2 solid. Let me add two waters because I need two oxygens on the right. That's going to be liquid. Okay. In bringing in two waters, I bring in two oxygens. Now I have to balance the hydrogen. Plus four hydrogens on the right because rule number 3D or 3C says add H plus where H is needed. Okay. So we're doing good. Okay. Moving on. Let's see what else. Rule number 3D. That's the one that I feel like is being done early, but I told myself I'm going to follow their rules. I'm not going to do my own thing and branch out to what I was taught in school. I'm going to follow their rules. So rule number 3D says for reaction done in base, it said here balance in base, right? Y'all can't see me write this. Balance in base, right? That means it says for reaction done in base, balance in acid first, neutralize H plus by adding moles of OH on both sides. Okay, so that's kind of doing it the way I was taught. Okay, so we've done the half reaction balancing, right? Let me make sure everything is balanced. So 2I minus and then I2. So at this point here, you can add the OH at this point if you want to do that. If you don't, I think you can go through here and balance the whole reaction in acid first, because that's kind of how I'm understanding this. You can actually balance the whole thing in acid first, then neutralize by adding OH in the end. I want to do it that way, and I know I just did not just go through and say I was gonna follow their way. I am. I have a different revelation of what they're saying here, that you can actually go through and balance in acid first, and then you can come back and neutralize each side by adding OHs. I want to do that because I feel like the math is a lot easier, and I am personally more comfortable with that. The way they do this stuff here, I'm not very comfortable with it. Okay, so y'all permit me to do this, and I'm going to be doing that. Let me go along like I'm balancing in acid. So let me continue from here. So I'm going to skip these steps right here, right? We'll come back to that. And then let me check, and now I'm going to be including electrons. So when I include electrons, I'm going to start with a check. On the left side, I have two negatives, right? Based on this. On the right side, I have nothing. Remember, we can only balance by adding negative electrons. So I'm going to add two negatives here. So now the right side matches the left. I'm going to add two electrons. So just bear with me here. And then on the left side here, I have one negative, but I have four positives. Plus, plus, plus. I should have written this smaller. Maybe I should write on the bottom because I know. I'm like, I'm going to follow the rules, and when I got here, I just couldn't do it. It's just, it's, it's harder for me to do things in a way that's not very natural to me. I know. That's why I don't force you guys to do something my way. I always say, if you have an alternative way that works for you, go with that. Because it's just, yeah. So negative here, positive. One, two, three, four, right? And so this neutralizes that. So now we have an excess of one, two, three positives. So we want to make the left side match the right side. The right side has no charge. This is just zero. So we need to have three negatives here to make the left side match the right side, right? So that means add three electrons. Now we're going to try to make sure that these are even. To make sure these are even, multiply this by 3, multiply this by 2 to make the electrons at least match. We're trying to balance the charge, right? Step number 5, balance half electrons by adjusting electrons. That's when you multiply the coefficient by a number to make the oxidation side match the reduction side. Okay? So in doing that, I end up with, let me see, I can remove these. These are just helpers and means to an end. So multiply the top part by 3. Let me do that. 6, oops, 6 electrons, 3, this is going to be 6, right? Because if I multiply by 3, it becomes 6. Multiply this part by 2, this becomes 4, 2, 8, 2, 6 electrons. Okay, so hopefully I got everything correct. Okay, so when you do that, let me check before I continue. 6 I's, 3 times 2, 6 I's. 6 electrons. Okay, this is 6 electrons, 6 negative on the left side. Here, 6 negative plus 2 negative makes 8 negative, plus 8 positive makes neutral. On the right side, you have no charge. 6 electrons, 2 MNs, 2 MNs, 8 O's, 4 O's, 4 O's, 8 O's, 8 H's, 8 H's. So it's the half reactions are balanced, right? Now let me go ahead and add the whole thing. Okay, let me add the whole thing. This part and this part cancels out. We get 6I minus AQ plus 2MnO4 6I minus AQ plus 2MnO4 minus plus 8HAQ to give us 3I2 AQ plus 2MnO2 solid plus 4H2O liquid. Okay? So this is balanced. Ooh, this is balanced in acid. Okay? So I'm kind of going by balance all the way to the end in acid first. Then go back and neutralize by adding OH. So this is balanced in acid, right? Like I said before, BIA. Now I'm going to actually balance in base. To balance in base, you add 8 OHs to both sides, right? You're trying to neutralize this to make water. It's going to be less adding, less subtracting. So it's going to make 8 waters, okay? So I'm going to write this out as 8 waters. So now we have 6I minus AQ plus 2MnO4. These consolidate to form water. So plus 8 waters to give us 3I2 plus 2MnO2 plus 4H2O plus 8OH minus. Okay, so now that we have, oh, sorry, step is out of the way. Now that we have here, we have to consolidate any H plus, OH minus, and water present on both sides. Okay, so we're consolidating. So I still am following the rules. I just kind of interpreted part D differently by balancing all the way in acid first and then adding the OH to both sides. So that's how I'm interpreting that rule. And that's kind of how I was taught it when I was in school. So let's see, where are we at right now? So we want to find where we have H2O on both sides and any OHs, right? So right here, let's see if there's anything to consolidate. I have 8 waters here and I have 4 waters here. I do see OH here, but I only see OH on one side. So what I'm going to do is then minus 4H2O. So you subtract the lesser amounts from both sides. I feel like this way is a lot more smooth than doing it the other way I was doing it, where you add too many waters and you move stuff around. That was just too much. Okay. So here we have 6I minus AQ. Sorry, I just got an email there. I'm checking the email. Ooh, stuff we do. MnO4 minus plus 4H2O. Okay. Since this one here got used up by that, that cancels out. We're left with 3I2 aqueous. And we'll double check to make sure that what we have in the end works, right? And then plus 8OH minus. I'm getting a reminder to stand. I'm literally standing right now. Okay, let's check to make sure everything is okay. So as far as charges are concerned, I have 6 minus added to 2 minus on the left side. On the right side, oh, plus 0, which makes a total of what? 8 minus. On the right side, I have 0 from here, plus 0 from here, plus 8 minus from there. So really, I have 8 minus equal 8 minus. So the charges are balanced. No, okay, woo, that was close. That's what I like about this, right? When you write on this quote unquote board, if you make a mistake, just go back and then everything displays. On the real board, when you make a mistake, you can't just press back, right? Okay, let's see. Number of atoms. We have 6I. We have 3 times 2, 6I. So that's balanced. We have 2 MNs. We have 2 MNs. So that's balanced. We have 8 O's plus 4 O's. So we end up with 12 O's. Let me see here. You have 4 O's from here and here plus 8 O's. So we end up with 12 O's. Yep, balance. And then if that balances, the final one should balance, right? So here I have 8 H's. And then here I have 8 H's. Yep. So everything balances. I'm sorry, this is not so neat. Let me show you theirs. Theirs is so much neater than mine. Actually, maybe I can show it over here since it's the same slide. Yeah, this is theirs. Very organized. And they have it right here. So it shows the balance. 6 I's, 8 H's, 2 M's, 12 O's, and then you have the charge here. Okay. These look very similar, but this is a different problem from that one. Yeah. So I'm gonna balance the last one, which is this one here. Oh, sorry, I need the directions right there. What am I doing? I just got distracted. This would be my last one, the last one I'm balancing, right? Because I'm already telling that the fatigue is kicking in. And once I get fatigued, that's when I start making all these mistakes. So this will be the last one, and then when I get done from there, we're going into the application of electrochemistry, and this will be our next class, okay? So this is like video number 2. So balancing in Bayes. In balancing in Bayes, let's see, this is our last one. This is where I kind of got stuck in lecture yesterday, and we stopped right here. So balancing in Bayes, once again, follow the directions. Assign oxidation numbers. This would be -1. This one here is -2 for each oxygen. So we end up with -8, but this is plus -2. This has to be +6, right? +6 right here. For each chromium, -2 for each oxygen. So chlorine has to be +4, right? Because these oxygens, you have -2 to make -4, so chlorine has to be +4. Okay, and then you have +1 for each hydrogen, right? But there's 4 hydrogens, +1, +1, +1, and then each oxygen is -2, -2, -2, -2, right? So when you look at this, there's 4 of these. So what must chromium be for the whole compound to be 0? So you want to kind of total this, right? +1 +1 +1 +1 is what? Is +4. And then -2 -2 -2 -2 is -8. So when you combine these, you end up with a total of -4, right? So essentially, chromium has to be +4. That's one way you can look at it. The easier way I like to look at this, oh, this is out of frame. The easier way I like to look at this is you recognize hydroxide from 1411, right? You should. If you don't, you should. each hydroxide ion is -1, right? And if the compound is neutral, that means chromium has to be +4. And I like to use that way because I feel like it's a lot easier. So you have +4 for chromium, -2 for oxygen, +1 for hydrogen, and that's how we get that. Okay, now let's check. Chromium is changing, going from +4 to +6. That's going to be your oxidation right there. I'm doing a quick check. -2, -2 for oxygen. Oxygen is not doing anything. Hydrogen +1. Oh, there isn't even a hydrogen product. Ooh. And we're balancing in base, right? And then let's see. Chlorine is +4, +4, 2 minus. Oh, come on. +4, 2 -1. Okay, so this is your reduction right here. Okay, so we'll go ahead and write our oxidation and reduction half reaction. So oxidation first. CrOH4 gives us CrO4 2 minus. Okay, and the next one, ClO2 gives us Cl minus. So let me go ahead and erase it so this is not confusing right now. We know what is oxidation, what's reduction. So I want to make sure I have everything copied over. So this is oxidation. This is reduction. Have I left out any sign? No, I don't think so. Okay. Now let's go through and follow the rules. I've done this part, number 2. Number 3 says first balance half reactions by mass. First balance elements other than hydrogen and oxygen. Okay. So real quick, I have one chromium here, one chromium here. One chlorine here, one chlorine here. My non-oxygen, non-hydrogens are balanced, right? And number B says add water where oxygen is needed. So over here I have 4 oxygens, and on the right I have 4 oxygens. So my oxygens are good. And then for the same reaction, let me finish that part before I continue. Add hydrogen where hydrogen is needed. So I have 4 hydrogens here, right? But I need 4 hydrogens. I'm going to add 4 H pluses here. Do I have enough room? Yeah, I think I do. Let me move this over. OXRED. Okay. So I want to make sure I balance everything because this is in class. I usually have safeguards in place because I know how I get tired and what else. I didn't do that yesterday. I didn't follow my safeguards. So checking real quick. Chromium, chromium. 4 oxygens, 4 oxygens, 4 hydrogens, 4 hydrogens. I didn't do that yesterday, and I feel like that's where things went wrong. Okay, so I have chlorine, chlorine here. Now check once again for the second reaction, reduction. Add water where oxygen is needed. I need 2 waters on the right to supplement for the oxygens that I need, right? I need 2 oxygens on the right. I added 2 waters. That's rule number 3B. Add H plus where H is needed. Now I need, I'll put here 4 H's on the right. Yesterday I was fixating on these two canceling each other out, but you have to balance electrons first before you even try to compare, right? Okay, so this is what I did essentially. Okay, so then before we continue, it says for the reaction done in base, balance first in acid. So I'm going to actually go all the way to the end and balance in acid. It will make my life so much easier. Then I'll neutralize both sides, right? So I won't even deal with step number D yet. I'll come back here. Same thing with this part here, okay? I'll deal with that later on after I have tried to do everything else. So 3D and 3E, I'll put a pause on that for right now. Come back to it. So next I'm going to include electrons. So to include electrons, before I do that, let me make sure this is balanced. One chromium, 4 oxygen. I think I checked already. So I can move on, right? Electrons. So electrons, I got 2 negatives here. Negative, negative. 4 positive, 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 positive. Okay. So if I do this, I have a net of 2 positives on the right. But the left has just 0. Since I cannot add positive charge, I have to get rid of the positive charge by bringing in 2 negatives to get rid of these. That's plus 2 electrons. Okay? And then on this side, I'll leave that here for right now. I have 4 positives. 1, 2, 3, 4. Right? I have 4 positives on the right side, but I have 1 negative on the left side. We can only add negatives. We can't add positives. And usually in the reduction reaction anyways, remember the electrons are on the opposite side of the oxidation. So we know we're adding electrons on the left side, right? Correct. Left side only, not right. So I'm going to add negative, 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 negative. If I add four negatives, it neutralizes these four I already have, but I have to add a fifth negative so that now I have one extra electron on the left side to match what I have on the right side. One negative on the left and one negative on the right. So I added 5 electrons in the process. Okay. So now my charges should be balanced and so should my on the half reactions, right? And the atoms. Now I'm going to go through here and it says balance balance half reactions by adjusting electrons. So for this part here, I'm going to multiply the first reaction by 5. So I'm going to write it up here so I can see it, times 5. Then multiply the second reaction by 2, okay, to make this 10 and make this 10. So I'm going to put 2 here, 2, then I'm going to put 8, and this is going to be 10, right? 2, 4, correct? And then here, times 5. 5, 5, 20, and then 10. Okay, did I do this correctly? 5 CR, 5 CR. 5 times 4, 20 O's, 20. Oh, 5 times 4, 20 O's. 5 times 4, 20 H's. 20 H's, right. So it looks like now I got things where they should be, right? Let me just change. This is 20 H's plus 20 H's. These are 20 H pluses. Let me, because it looks like two OH's. 20 H plus 10 electrons, okay? I think I feel better about the numbers now. The 20H plus, not 2OH plus. It's kind of weird looking. Okay, now that I've done that one and I feel better about this, I can now go ahead and add these two half reactions because the number of electrons match and then the half reactions are balanced. So add these two, and what I'll get is this cancels out with that, and I end up with, I'm going to write it here, 5 CrOH 4 plus 2 ClO2 plus 8H to give us 5 CrO4 2 minus plus 20 H plus 2 Cl minus plus 4 H2O. Okay? So once I have this, let's see. Oh, I need to consolidate my H pluses. So I'm going to actually do this part here, consolidate my H pluses. Because here I have some H pluses on the left and on the right, right? Correct? These right here. I have some here and I have some here. It would actually give me less to write. So let me go ahead and do that. I'll subtract this lesser part on both sides. So minus 8H here. So this goes off completely and I end up with 12H pluses on the right, 5 CrO4 2 minus plus 2 Cl minus plus 4 H2O. And on the left side, I have 2 ClO2 plus 5 CrOH4. Okay? So right now, this is balancing acid. So with balancing these reactions, I like to balance an acid first. So this is why, that's how I interpret this, because this is how I learned it. Balance an acid first, and then neutralize the moles of H plus by adding OH on both sides. So once you have balanced an acid, then you add OH, the same number of OH to both sides of the equation. So 12 OH here plus 12 OH here, and then go from there, okay? So essentially now these two combine to make 12 H2Os, right? Because H plus OH make H2O. So let me write the right side first. 5 CrO4 2 minus plus, this gets replaced by that, 12 H2O plus 2 Cl minus plus 4H2O. Did I get them all? 1, 2, 3, 4. And on the left side, we have 5CrOH4 plus 2ClO2 plus 12OH minus. Okay? Now, we're going to consolidate. This combines with this because they're both waters, right? If they're on opposite side, you subtract the lower amount. So we end up on the right side once again. 5CrO4 2 minus plus 2Cl minus plus 16H2O. And I'll double check my math to make sure everything is correct. 5CrOH4 plus 2ClO2 plus 12OH minus. Okay? This looks like it's balanced in base, but let me double check. Sorry, this is not straight. Once again, you want to go ahead and check to make sure that the number of atoms are equal on both sides of the arrow, the yield arrow, and the total charge is the same. So I'll start with the reactant side versus the product side. So remember, these have to be the same. Let's start with the charge. For our charge, you can see this is essentially 0, 0, and then I'll say here 12 negative, right, on the left side. So a total charge on the left side is 12 negative. On the right side, I have 10 negative, 5 times 2, 2 negative, and then 0. When you total that, you get 12 negative. So the charge is balanced because both sides of the equations have essentially 12 negatives. Okay? Now we're going to be looking at the atoms. I'm going to start with hydrogen, go to oxygen, and then end with chromium. So I'm starting from the hardest to the easiest. Okay? So I'm going to pick a color. I think I'll start with orange. Hydrogen is going to be my orange. So follow the colors as I go through trying to find the numbers. How many hydrogens do we have? We have 5, correct? Times 4. So I'm seeing 20 from the first compound. From the second compound, we have none. From the third compound, or the third formula, we have 12. Y'all see that? Hopefully you can see right here. Hydrogen, 12. So when we add this up, what do we get? 32 on the reactant side. Oops, on the product side, let's see. This one doesn't have any, so that would be 0. I'll write 0. This one here doesn't have any. That will also be 0. This one here has 16 times 2 to 32. So we have 0 plus 0 plus 32. Sorry. It's my hands. My hands are all over the place. So we have 32. So our hydrogen is balanced because we have the same number of hydrogen on both sides of the equation. Next one is oxygen. For oxygen, I'm going to pick a green color. Oxygen is like hydrogen having this right here, 5 times 4. So oxygen also has, for the first formula, 20, right? So it's going to be 20. Second formula, 2 times 2, 4, right? Third formula for hydrogen is this one right here. We got 12. So it's 32 plus 4, 36. Okay? On the product side, 5 times 4 oxygens make 20 from the first formula. We have 20 oxygens here. Second one doesn't have anything. Third one has 16. 20 plus 16 makes 36. So this matches this, so it's balanced. So the hydrogens are equal on both sides of the equation. Oxygen matches, so the last one, chromium, should match, right? So let's see chromium right here. Let me use a different color. Oh, I guess to be consistent, the oxygen was green, 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 right? Last one we're going to be looking at here will be, hold on a second, that will be chromium. We have 5 chromiums on the reactant side, and we have 5 chromiums on the product side. So it's going to be 5, 5, 0, 0, 0, 0, right? So 5, 5, 0, 0, 5 plus 0, 0, 5. Okay? So yeah, since the number of atoms match and the charges match, we have a balanced equation. And the balanced equation is essentially 5 CrOH 4 plus 2 ClO2 plus 12 OH minus to give us 5 CrO4 2 minus plus 2 Cl minus plus 16 H2O. Okay,